So, a very good afternoon to all of you. In today's class, we are going further from image sensing and acquisition. We were discussing the model of digital image, how the model can be created. We are going to take that forward today. Sampling and quantization we have already discussed, but we will discuss a little more about them. And then we are going to talk about the resolution, the spatial resolution today, and grayscale resolution. So we are going to talk about all those aspects in today's class. So, in the last class, we have understood that how how an image can be quantized and then digitized. The word quantization means in the XY plane, you are you are dividing the entire image into certain number of points. And then since an image is a two-dimensional construct, an image is generally a two-dimensional construct. I'm not getting into a special case of one-dimensional and a three-dimensional construct. Remember, present day we are doing 3D printing and all, where the entire data goes in a three-dimensional construct. Forget that for the time being. In our course, we are focusing mostly on two-dimensional images. Sometimes to understand certain phenomena in an easy manner, we also stick to one-dimensional images, but that is again not very often used. So most of our images will be two-dimensional images. So in a two-dimensional plane, we try to sample the image into some number of points, and if I call the top left point as my 0, 0, then I can have n number of points along the horizontal and say n number of points along the horizontal and m number of points along the vertical. So when I say, now you have to listen to me carefully. When I say n number of points along the vertical, that means the image has been sampled into n number of columns. So this is one column, this is another column, this is next column, and so on and so forth. The columns are traditionally numbered from 0 to n minus 1. So when we say it is if number of columns is n, then the addresses of those columns are starting from 0 to n minus 1. You will need this while doing practical, so please remember. Similarly, the horizontal sampling results into number of rows of the images. So you can have m number of rows. This is the first row, second row, third row, fourth row, etc. And again the counting begins from 0 and ends at m minus 1. So when we say that there are m number of rows, we mean that there are starting row is 0 and the last row is m minus 1. The center, the origin is not center. Remember, origin is this point, which is 0, 0. Any pixel can be obtained by a running index I and j. So this can become an ij pixel. The coordinates of the center can be obtained by this formula. You divide the number of rows m by 2, number of columns n by 2, and if m and n are odd numbers, then you know that this will generate into some decimal number. Then you floor it. That means you take the lowest of the decimals. So if it is 3.5, for example, then you take 3. So that becomes your center. If it's an even number, then the calculation would yield a round figure. no decimal number, and then that would remain as the center. So now I can transfer this entire plane into a matrix plane where the number of rows of the matrix are same as number of rows of the matrix are same as the number of rows of this image, and the number of columns are also same as, I think in this representation it has been reverted. So number of columns are represented by number of rows here, and number of rows are represented by number of columns. So you can see that starts with 0, 0, and the last element is n minus 1, m minus 1. So this entire thing can be transported to this matrix form. The reason for this inversion could be that here x-axis is on the vertical, here x-axis is on the horizontal. So each location in this matrix corresponds to the location of a pixel in the image. So 0, 0 is here, and n minus 1, n minus 1 is here. Now, what is the value of each location here? So the value of each location, as we have already seen in the last class, is a function of position. So at different position, you will get different brightness or intensity values, and those values will be written at these positions. A more simplified version can look like this, or right from here you can take. So it can be simply a matrix with some values a00, and once it is quantized, once these brightness values are quantized, then it simply becomes those quantum values. So number of grayscales required are generally 2 power k. Now let me explain this to you. K is an integer. For example, if you have a binary image, now what is a binary image? A binary image is something where the numbers are written in terms of ones and zeros. So only two elements are used, either 1 or 0. 1 is bright, 0 is dark. So if you use only one bit to represent your gray level, then you will get 2 power 1, k is number of bits, so 2 power 1 number of gray levels. So L, when I say number of gray levels, the number of gray level is L, 2 power k, where k is the number of bits. So if you use 1 bit, then 2 power 1 is 2. You get 2 gray levels. If you use 2 bits, then 2 power 2, you get 4 gray levels. If you use 3 bits, if you remember last lecture, we have seen a 3-bit example. So if you use 3 bits, you get 2 power 3, which is 8 gray levels, 0 to 7. If you want 256 gray levels, then how many bits do you need to use? If you want to have 256 gray levels, then number of bits to be used are such that 2 power k should yield 256. So you can calculate, it's 2 power 8, k will become 8. I can always ask you a question, why this 2 is there? Can anyone text and answer me back? Why do we use 2, and why not 3, why not 5, why not 10? So let me see if anyone knows. In the meantime, I can talk a little bit further. Levels are discrete. So all these levels are, they have a separation. So it will be 0, 1 or 0, 1, 2. You will not get a level like 0, 0 0.1, 0 0.2, 0. You will not get those kind of thing. You will get levels are discrete, that is separated. Their levels are equally spaced, and they are integers between 0 and L minus 1. So again, the intensity levels are, although this will generate certain number of intensity levels, they are counted from 0 to L minus 1. So if you have 8 levels, you will start counting from 0 to 7. If you have 256 levels, then you start counting from 0 to 255. Not necessarily. Chintan, we are not talking about binary image particularly. If it is binary, if k is equal to 2, then it is binary. Why is the 2 here? Not because it is 2D image, no. Somebody is saying, Pinak, you are saying that we are using the base as 2. Yes, we are using the base as 2. But that is precisely my question. That why are we using the base as 2? So think about it and let me see if anyone can answer. Sometimes you will hear this term called dynamic range. If you look at the latest um phones, particularly iPhones and Samsung top end phones, they all talk about high dynamic range or HDR photography, HDR video, etc. etc. So typically the dynamic range means the number of values of grayscales. So if it is going from very dark to very bright with more number of intervals, then we say that it has a high dynamic range. And if it is less dark, less bright, and less intervals, then it is called low dynamic range. So this is one term you will often hear. Yes, Mamta. Mamta, you could be partly correct. It can be zeros or one. My question was that only, that why could it be zeros and one only? The answer to the question is that the modern day computers work on binary. That is one of the major reason why we take this base as 2. Most of the computers today, they are working using binary number systems. Otherwise, if you have to if you don't have to use computers, if you have to use manually, then you can write any intensity value by number and add and subtract. But unfortunately, it becomes too big a task for humans, and if computers has to do it, they understand only binary. Or even though at the surface you may feed any number, at the software, at the machine level, they learn and understand only binaries, and that is why this base is 2. Okay, so I will get back to this equation in a while, but let me go ahead. How many bits will be needed? So you can now see that the number of bits needed for a given image is m into n into k. So number of bits used. So m into n will give you number of pixels in the image. Remember, one is the number of rows, other one is number of columns. If you multiply the two, you get total number of pixels. Multiply that by k, which is number of bits used to represent each pixel. All the three multiplied together gives you total number of pixels. So the total number of pixels has to be given by this expression. We will take some special case. What happens if it's a square image? That is, m is equal to n. So if m and n are both are equal, then it becomes n square k. If there are k or 2 power k gray levels, then such an image is called k-bit image. This image is normally referred as k-bit image. So that is another term that you will hear many times. 8-bit image, 12-bit image. Present day industry, professional photographers, they work in the range of 12-bit to 16-bit images. Most of the normal cameras, they work between 8-bit to 12 bits. This term is also called a bit depth. How much, how many bits are used is also referred as bit depth. So that is something you will hear sometimes here and there. A 14 gray level means you need to have 4 bits, as we have already discussed. 256 gray levels will have 8 bits. And here I have a big chart which actually shows how the number of bits increasing and number of pixel increasing will increase the memory requirements. So on this side, this is number of bits. If number of bits is 1, levels are 2, 0 and 1, remember. If number of bits 2, levels are 4, 0, 1, 2, 3, so on and so forth. If number of bits are 8, the number of levels are 256. They are counted from 0 to 255. Now, suppose if I have a third, and this is n, 32, 64. So I have a 32-bit image. Sorry, I have an image which whose number of rows and number of columns both are 32. So look at the memory requirement. So it has 32. It has 32 width and 32 columns. So number of pixels will be 32 into 32. If I use 1 pixel representation, then I will multiply by that one. So 32 into 32 into 1 will give you 1024. Typically, if you use for the same image, if you use a 2 pixel representation, then it will get doubled and it will go on increasing. So for example, look at the last case. I have an 8000 rows and 8000 columns approximately. So if it is 8000 rows and 8000 columns, I'm using approximate, 8192. I'm rounding it off to nearest 1000. So 8000 into 8000 will give you 64 into some number of zeros. If you calculate carefully, it will be around 6.5 megapixel. So if you have 6.5 megapixel, and if you are using an 8-bit coding, that means to represent each pixels, you are using 8 bits, then this is going to be your memory requirement. These many bits are needed. Okay, so you can see that this is 3, 3, 10 power 6, 10 power 8. This is 5.38 into 10 power 8 bits are needed. Okay, these are the bits. The commercial photos gives you the size in bytes, not in bits. When you go and buy the memory, you get in bits. You get in bytes. So when you get say a pen drive, say 64 GB, when you say, so it's gigabyte. It is not bit. So my question is, how many bits form 1 byte? Can anyone tell me? Think about that and tell me. But here is the memory requirements. As the number of bits increase and number of pixels increase, the memory requirements shoot up. Towards the later part, I will show you in general that the image becomes clearer and more visually appealing if both N and K are high. So memory requirement is an ever increasing phenomena. You will always need, you can always increase N and K and say that the image looks better, and therefore that graph is important. That is how it has increased over the years. Yes, it is 8 bits form 1 byte. So here it is b by 8 into 10 power 6, and that is how your memory requirement. So if you have, let's say, here it is 10 into 10 power 3. So if you have 1000 pixel by 1000 pixel image, and if you are using say 100, uh, and if you're using 8-bit coding, then it can go up to 100 megabytes. That is what it means. That brings us to the next idea, and that is called resolution. Now here in this image, what I'm trying to show you is the image is the same, but it is at reducing resolution, starting from 1024 by 1024 here, and going up to, I guess, 32 by 32 resolution here. So 1024, 512, 256, 128, 128, 64 and 32. So if I keep the image size the same, and for that, so if I keep the image size the same, and for that I need to extrapolate, because the sizes do become small as you reduce the resolution. So to keep the size same, you need to do some extrapolation. So I would leave you people to read more how to extrapolate. It is given in the reference. So please go through it. So you will find that up till here there's no noticeable difference. But as you come to this, you will find that the edges are now little bit zigzag. Here it is more. Here it's very difficult to find with the details, and here it is extremely challenging. You cannot make out what the image is. So this is what happens if your resolution drops. This is called dropping in the spatial resolution of the image, and as a result, what in common layman's term we call pixelation happens. What happens here is pixelation. Here is the actual impact. So if you allow pixelation to avoid, then as you reduce the spatial resolution, your image size drops consequently. So you can see that it looks as the same here also as it looks here, but the size has reduced. This is a more practical. So for example, an image which does not have any pixel, if you see it on a small screen, can look very poor in a large screen. That is why most of the photos which you can take with your mobile phones, if you ever printing them in large sizes will give you very different results than what you see on the mobile. Or for that sake, you see an image in your mobile phone, you transfer the same image on a TV set. If you have a TV set which is say 32-inch or 44-inch, try watching an image on that large set, you will see the difference. Now, that was spatial resolution. Now I'm going to talk about the gray level resolution. You remember the last class we showed this diagram where I showed you that these are my gray levels, and there were 8 gray levels starting from 0 ending at 7. So these were my gray levels, and using these gray levels I had quantized the intensity values from this image. And this is the result we had obtained. This was the result we had shown. I had shown you along this line. That means roughly I had shown you this line. But this line will can be drawn, redrawn at multiple places, and you can get all the places. And you can see that it's not very clear. So we are going to look at the impact of gray levels on the image. Remember that this is an 8 level image, 0 to 7. That is 3-bit image. And then we can go ahead and look at the impact of other levels. So look at this. I have 4 images here of a woman. You can see that 8-bit, you can see there is no much discoloration or anything. But the moment you go to reduced number of bits, you will find that discoloration happens. If you are watching this lecture on laptop, you will find that the skin tone at the shoulder goes on changing. This is a little bit flaky here. It is much flaky over there. Eventually, if you go on reducing and if you bring it to 2 bits, then you will find that it is largely black and white. I'm sorry, this has to be 1 bit. This shouldn't be 2 bit. This has to be 1 bit. So it's either 1 or 0. So wherever you are getting white, it's all 1. Wherever you are getting 0, it's all black. So you are reducing an 8-bit image into a 2-bit image. I'll show you another example where the impact of reducing the gray level. So this is a 32-bit image. It has a very high bit depth. 32-bit is a very high bit depth. Very top-end professionals work in this bit depth because remember, I will show you later that more the bit depth, more the memory requirement that we have already seen, more is the computational requirements, challenges, and even higher will be the sharing the image over the network. So very high-end professionals work in 32-bit domain. What happens if I reduce the number of bits? So you can see I'm moving to 16, 8, 4 and 2. At 16 you will find that some sort of loss of information is happening in the skull area. This has become what is a smooth transition from center to the periphery is no longer a smooth transition. From here to here, all the gray levels are same, but there's an abrupt jump. The gray level drops. Again, it is same up till here, and again abrupt drop, and so on and so forth. If I reduce it further, then you can see that what is seen here as 1, 2, 3, 4 levels has now dropped just to 2 levels of gray, which is eventually spreading into just 1 gray level. And finally, you get to binary levels, 1 and 0. So reducing resolution. So to summarize this discussion, the resolution have two components. One is called spatial resolution, and other one is called gray level resolution. So if anyone asks or anyone discusses what is the resolution of an image, you must ask this question, that which resolution are you talking about? Are you talking about gray level resolution? Are you talking about what you call intense spatial resolution? Depending on what resolution you are talking, you will get into results. Now we look at some basic relationship between the pixels. So neighbors of a pixel. A pixel can have neighbors in many ways. First of all, we can say 4 neighbors. So any pixel xy has 4 horizontal or vertical neighbors. So the two horizontal neighbors will be x plus 1y and x minus 1y. That is one to the right and one to the left. And then one above, that is xy plus 1, and one below, xy minus 1. So these are 4 neighbors, and they are also referred as 4 neighbors, and it is called a set N4. Whenever we write in DIP, whenever we write a set N4, means we are looking at four neighbors which are left, right, and top, bottom. These sets can be utilized to figure out many important properties of an image, including the boundaries of the image. So for example, how would you define the boundary? How do you define the right boundary? So if an image has this, if an image does not have this pixel, that means it is at the right boundary. If an image does not have this pixel, or if a particular pixel does not have this one as a neighbor, then it is the left boundary. If a particular pixel does not have this as a neighbor, then it is the upper boundary. What happens if it is in the corner? So if it is in the top right corner, then it will not have the pixel which is above it, that is which has a coordinate x, y plus 1, and it will not have a pixel to the right of it, that is x plus 1, y. So on and so forth. So these are the four neighbors. And then there are diagonal neighbors, which is a set called ND of any pixel. So any pixel P has four diagonal neighbors. So it is all the diagonal sides. So x plus 1, y plus 1. Remember xy is my original pixel. X plus 1, y plus 1, x plus 1, y minus 1, x minus 1, y plus 1, and x minus 1. So all four corners. So these are horizontal, vertical, four sides are four neighbors. Four corner neighbors are called diagonal neighbors. And then a set which consists of all the points from this and this, they are called 8 neighbors. So there are something called as N8 set. So that is how a neighborhood of a set of a pixel is defined. Now we can look at the connectivity between the pixels. So connectivity is important. Most of the image processing algorithm situations uses the connectivity between the boundaries of objects and components of regions in an image. So suppose if you want to make, say, a face look brighter, so you have to figure out the face pixels in an image which are connected by some law. So there can be four neighbors next door, or so if they can be adjacent. Two pixels are said to be connected if they are adjacent in some sense. Now that sense needs to be defined on a case-to-case basis. So for example, there can be four neighbors, there can be diagonal neighbors, there can be 8 neighbors. So depending on whatever is the case, you can define the adjacent pixels, and they should also be related to each other by some gray levels. So that means, like, you would like to figure out two pixels which are adjacent to each other, but they should have the same brightness level, they are equal. So there we will say that they are connected. That means they are the part of the same subset of the image. For example, in a given binary image, in a binary image, we have two levels, 0 to 1. Two pixels, maybe four neighbors, are not considered connected until they have the same value. So binary, all the white pixels are connected, all the black are connected, but black and white, they can be a four neighbor, they can be adjacent to each other, but they are not connected because they are not having the same value. So here is one of the examples. This is four connection. So if I take this as P, then this is connected. This is four connect. We say that this is a four connected to this one, which is four connected to this one, and they are all having the same value also. So a path exists between the two. This is what is called a path. A path in an image subset is defined as the line which can be connected from one pixel to other in some way. So either it is 4 connected, 8 connected, or there's a third type of connectivity called mixed connectivity. So this is an arrangement of another arrangement of pixel, and this is an 8 connectivity part. You can see that this one, if you look at this and this, so this has a diagonal connectivity, which is a part of 8 connectivity. Now this is connected to this by a 4 connection, and this is connected to this by another 4 connection, and they all have the same pixel level. So this is connected to this one by a diagonal and 8 connection. So this is 8, these are 8 connected paths, while there is one more connection that occurs here. So this one, forget about this, this one and this one are connected in two ways. One is strictly 4 connection, so this way and this way, and another is the 8 connection, which is this way. So these are double connections. To remove one of the connections, we introduce something called as mixed connectivity, where we put some conditions by which we look at the larger path whenever these kind of double connectivity occurs. So you will take the larger path and select that and skip the smaller one. So this is called something called as mixed connectivity. Again, I would suggest you to read on 8 connectivity and mixed connectivity from the references. I will take a more important topic, and I think this is the last topic of discussion, that is the distance measures. So if you have 3 pixels P, Q and Z, and their coordinates could be X, Y, S, T and U, V, then D is a distance between P and Q. So between P and Q, D is a distance if it satisfies certain conditions. And that condition is the distance between P and Q has to be greater than or equal to 0, which is obvious. It will be 0 only if P and Q are the same pixels. Otherwise, it has to be greater than 0. The distance between P and Q is equal to distance between Q and P. So if you revert the arguments of the function, the value of the function does not change. So that way it is symmetric. And remember, I am choosing 3 pixels P, Q and Z. There are 3 different points on the image. The difference between P and Z has to be, or the distance between any 2 pixel has to be less than or equal to distance between the sum of or sum of distance between other pairs. So distance between P and Z has to be less than or equal to distance between P and Q plus distance between Q and Z. So it's like a triangle properties. You know, if P, Q and Z form a triangle, then one side of the triangle has to be less than the sum of the other 2 sides, except in one case where all the 3 points are lying on one line. In that case, the equality can come in. The Euclidean distance between P and Q, and now there are various ways of measuring the distance. The Euclidean distance is a normal distance formula, square root of x minus s the whole square plus y minus t the whole square, that you have learnt in your lower classes. And typically in an image where there are thousands of pixels, if you take a certain distance, then, and if you implement Euclidean distance formula, say for a distance of 5, then you get a circular patch or circular sub-image. So Euclidean distance formula gives you the circular sub-image. Then there's something called as D4 distance, which is called city block distance. So D4 distance is like 4 neighbors you can go from one neighbor to the other. You can go to right, you can go to left, you can go to top, you can go to bottom, but you cannot go to diagonal parts. So that is called a city block distance. Why is it called city block distance? That means if you are walking in a crowded city where lots of buildings are there, city blocks are building blocks. Each block has some buildings. Then to go from point A to point B, you cannot go diagonally because diagonally those buildings are situated. You can go left, right, left, right, left, right, that fashion. And that is why it is called city block distance. Typically, the distance between two pixels is given by x minus s, y minus t. We can see it in a simple diagram. So here is our diagram. This is my original pixel. Uh, if I have to, if my d4 distance is 1, try to understand carefully. If my d4 distance is 1, then I can go one up, one right, one left, one bottom. Sorry, one left and one bottom. So this. These are having d4 value equal to 1 from my center pixel. So these are the d4 distance 1 pixels. If I say my d4 distance is 2, then what are my pixels? So from here I can go 1, I can go 2. So this is my d4 distance 2 pixel. From here I can go here, here. From here left, further left. 2 steps now because I'm looking at a distance 2. 1, 2. But apart from these, there are some other pixels also. So I can go from here to here, that is my 1 step. But my D4 distance measure uses 4 neighbor pattern. So from here I can go here, but I can go here also, and I can go here also. From every pixel I can go up, down, right, left. Since I'm coming from left, I will not go to the left. I can already seen the right movement. I can go this way and this way also. Similarly, from here I can come here and I can go this way and this way. So these are my pixels which are also at a city block distance of 2 from the center. The last of the distance measure is the D8 distance, and D8 distance uses 8 neighbors. So where it can go straight, it can go diagonally, both the possibilities are there. We call it as the chessboard distance. So again, I would show you with the help of an example. So if you're here at this point, then you can go 1, 2. So this is the distance, D8 distance 2. Then you can go 1, 2. This is D8 distance 2. Yes. But look at some other fascinating thing. You cannot reach to this pixel by going from here to here and here to here. You will end your 2 distance quota at this pixel. But since it is a D8 distance, you can go diagonally. So this is 1 and then you can go right, and this is 2. So this is also at a D8 distance of 2 from the origin. Do understand that. Similarly, if you go 2 diagonal steps, you will get here. This is again at a D8 distance of 2 from the center. Okay, so you have to be careful. You can see that in case of Euclidean distance measure, you will create a circle. In case of D4 distance measure, you will create a diamond shaped structure around the center pixel from where the distances are being measured. And in case of D8 distance measure, you will create a square. Remember, this is a square, 1 2 3 4 5, 1 2 3 4 5. So you will create a square around the central pixel. So just by looking at the pattern of the image, you can guess what kind of distance has been calculated or measured. So we can stop here. Thank you.